Today's topic is about Big-Theta. So our next point topic is what's Big-Theta, or actually I would like to know what exactly this anything related to bounds are, or what can we say as uh, big O, big big theta, or big omega. All of three. They are called as asymptotic notations. So I would like to know what exactly the asymptotic notations are and how they are actually different from case analysis. So what are these? How is it different from case analysis? Not sure if it's a plural for that, but let's see. So big O, big theta, and big omega, they are different. How they differ from case analysis and how they're related. So they are called asymptotic notations. Asymptotic notations describe how algorithms run time, how an algorithm's runtime grows as input size n gets very large, which get closer to infinity. They ignore constants and low order terms to focus on scalability. So big O, or called as the upper bound, tells you the worst case growth or maximum time the algorithm might take. It's a guarantee. It will never take longer than this. Asymptotically, an algorithm runs in O of n square, then even in the worst case it won't take more than constant n square steps with some constant c used in worst case analysis. Big omega is the lower bound. Omega is the lower bound, so it describes the best case growth, the minimum time an algorithm will take. It tells us the algorithm take at least this much time for some input. So if an algorithm is having omega of n, then for some input it must do at least c of n steps. And big theta, tight bound, describes exact growth rate. It means the algorithm always takes roughly this time, no more or no less, asymptotically. If an algorithm is n log of theta of n log n, that means it grows exactly like n log n. In all cases, up to constant factors, used in average case or overall performance analysis. So this is the upper bound. This is greater than equal to function, and this is equal to function. Upper bound, lower bound, and exact bound, or the tight bound. So this seems more like mathematical functions rather than case analysis. Case analysis looks at algorithm behavior on specific types of inputs, not just how it scales. So as we had seen earlier, it tells the how a particular code runs with a particular input. So best case for lucky input, worst case for bad input, and average for all possible inputs. So key difference between asymptotic notation with case analysis. Asymptotic is for which n tends to infinity, and it has certain expressions. It's abstract and mathematical expression of bounds. This is practical behavior, and this is what generally happens in the coding round. So it's that's so far. And example is a linear search here, which has the best case O of 1 when x is at index 0. That means when I is 0 and n is 0, in that case I is less than equal to n. This condition fails and we directly return -1. So its omega is of order 1. Worst case, n. When x at n of not found. That means if n is some large value n, in that case we will keep running this up to n. So n times this function will run. So its worst case is of order O of 1. So its worst case option, big O, is of n. Average case, n by 2, half. is also n. So our theta is also n. So this gives us the asymptotic notation as well as the case analysis. So asymptotic is a mathematical language. That's why it has a word upper bound, lower bound, and the tight bound or the exact bound, or I call this exact value. But I would like to know how exactly it's an average case called exact, whereas something that generally takes as n is considered as upper bound, or rest all are called as lower bound. So how exactly is how is an average considered for an exact bound, or call as a tight bound? Isn't average just average? Because we cannot find an exact bound, can we? So how can an average lead to a tight bound? Isn't average as well an average, not an exact limit? So what is a tight bound, or a theta? Algorithm's runtime grows no faster than a function, which is the upper bound, and grows no slower than function, which is the lower bound. So if fn is a tight bound, the runtime always is proportional to fn in the long run, regardless of input variations. Average case means we consider all possible inputs of size and we can send probabilities to them. Assuming a known distribution, we compute the expected runtime across all those inputs. This is statistic expectation, not worst, not best, but expected time across all inputs. So how can average be equal to tight bound? Because in some algorithms, especially well-behaved ones, average case and worst case both scale similarly. The algorithm usually behaves the same way. An average is a fair statement. It means an average algorithm is proportional to a function and not just sometimes, but consistently across input space. Example is linear search, but not always. In some algorithms, average case differs significantly from worst to best. For example, in case of quicksort. Alright, but here we can see average case is n log n. That's how the runtime grows on expectation over all permutations of input arrays. Okay, in quicksort it is known to have the worst case of this, but in most cases it seems to run this way, and that's why it's considered a good sorting algorithm to choose for, because only in the worst of worst cases will it choose this, and that's very rare. So average is actually not same as worst case in here across most of the input values. So that gives us how the upper bound, lower bound, and the tight bound is defined. So I would like to ask, so are there any cases where average case or exact bound differs a lot from upper and lower bound both? Yes, definitely. Recursive XOR with both pivot choice, always picking last element. But here average and best case are the same, I believe. Okay, this is a really nice one. Hash table lookup, average case is O of 1. Even then, I think best case and average case is almost similar. Here also, best case and average case is almost similar. Best case, average case, worst case, infinite. Oh my god, which one is this? Pogo sort. Randomly shuffle the array until it is sorted. All three are wildly different, absolutely. Absolutely, all three are wildly different. So this is one which is very, very widely different. Rest all are quite similar in between best and average. So is it easy to find the average case in some cases? Like, don't we have to mathematically find the real averages for it? So it's more typical than best or worst case, right? Average case requires math and probability consider possible inputs, so we've got to have some equations. Interesting. So it's the case of linear search. Okay, we've got again the induction induction method of finding equations. Harder average case is the quick sort to prove it. We need reference relations and also possible positions, speed comparisons. Okay, average case is something practical but often ignored. We focus on worst case, so it's easy to analyze because it's a guarantee. In real world, average case is important, but it needs assumptions. Random data can be wrong. This assumption has gone wrong. So it's a case which is very realistic, but we rarely do. So I think we can ignore it, part of us. So that would be it for what's Big-Theta and how asymptotic is different from case analysis. Next we'll be moving on to the difference between omega 1 versus big O of 1. I think we have cleared this part, because how they're different is omega is the lower bound, which means the worst case analysis asymptotic notation, whereas the big O is the upper bound and it is the asymptotic notation for the best case. So lower bound, upper bound, theta, right? So that would be it for and next we have what are amortized analysis. So I think we'll be up to it next the next video.